All right. In the last class, we defined the exergy, and we also talked about the reversibility and irreversibility of a thermodynamic system and how it's contributing to determining the exergy or useful work, right? So today we are going to talk about the topic 8.3, which is second law efficiency. Second law of efficiency. So let me give you two different example. Okay, so these are high temperature thermal reservoir source at 600 Kelvin and another is 1000 Kelvin, and then a heat engine, right? Both a heat engine operating between these two source and sink. So this sink temperature is 300 Kelvin and this sink temperature is also 300 Kelvin, right? So this engine A and this engine B. So thermal efficiency of engine A is 30%. However, the maximum thermal efficiency, considering there is no loss, right, and there is no loss and reversible or ideal case, the maximum thermal efficiency of this system equals to 50%. And similarly, the thermal efficiency of engine B equals to 30%, and maximum thermal efficiency, right, maximum thermal efficiency is 70%. And we can show you quickly how it's becoming 50% and 70%, right? So for example, the thermal efficiency, we know that T1 minus T sink divided by T T sink divided by T source, right, which is 1 minus, so in this case, first case, it is sink is 300 Kelvin divided by 600. So basically, if we solve it, it will be 50%, which is this one, right? Similarly, we can show that for this one ideal case, the efficiency will be 70%. Now in real life condition, that's not the case. In real life condition, what is happening is there are some loss, right? So basically, this efficiency law we saw in chapter 5, we defined this efficiency based on the first law of thermodynamics, right? Or we call it first law efficiency. However, they're not helping us to determine that, how much the actual efficiency or how those engines are behaving, right? If there is any loss, then what is the impact or what is the useful efficiency or useful work generated by this engine. So that's the time this second law efficiency plays a vital role, right? How the second law of efficiency, which is defined by eta 2, is equals to the ratio of the thermal efficiency, right, eta thermal efficiency of that engine, and ratio of the thermal efficiency in reversible. We know that this is the ideal case, right? Ideal case. So when we compare something with ideal case, then we can say that how much is deviating from the standard condition, or how much is we are achieving, or how much we are deviating from the standard condition. So that's the definition of the second law efficiency. Now the second law efficiency, you can see that this thermal maximum thermal efficiency 50% here, 50%, this one maximum thermal efficiency, and 70%, these are misleading. How? Let me show you. So the thermal efficiency for case 1, or the second thermal efficiency for case 1 will be, the thermal efficiency is 30%, right? 30% or 0.3 divided by the divided by the maximum equals to, or the reversible, which is equals to 0.5. So the ratio will be 0.6, right? That means 60%, 60% efficient. However, you can see that it's saying that it will it will give us the maximum 50%, so which is not right? So we are getting 10% more than in the ideal case. So that's the actual, or that's the useful maximum possible amount of efficiency we can get from the engine A, right? So for engine A. Now for engine B, let's take a look whether it's, let me show you, it's engine A and engine B. Okay, so heat engine B, the thermal efficiency is 30% and the maximum thermal efficiency is 70%. So 0.30 divided by 0.70, and we can see that this efficiency is actually 0.43 or 43%, right, for engine B. That means this information is misleading. So we are getting only 43% of useful work from this device, or only 43% of energy from this system. However, this system is, the actual case, ideal case, it's telling us that it will produce up to 7%, 70%, which is kind of misleading. So that's the time this second law of efficiency playing the role. So that's the definition of the second law of efficiency, which is nothing but the ratio of the thermal efficiency divided by the actual ideal thermal efficiency. Ideal means that, of course, this system has to go through the reversible process. Now if we define that the same second law of efficiency, which is eta 2, in terms of work, then we can define useful work divided by reversible work, which is the maximum or ideal, right? Reversible work. So this definition is only applicable for work producing. For example, work producing is turbine, right, or piston cylinder, right? What if I ask you guys what is the efficiency of second law of efficiency for work consuming device? So in work consuming device, we know that W reversible is always smaller than the W useful, right? W useful. So in that case, useful is the input, and W reversible is the output. So this is the work consuming device. For example, what are the work consuming device? Compressor, right? So compressor, or maybe some part of refrigerator, right? So in that case, it will be the definition will be this. So this is for work consuming. And also some people also there is a definition for, in the case of refrigeration or air conditioning system. So what is this? So coefficient of performance divided by coefficient of performance of reversible cycle. So this is for refrigeration cycle, right? Refrigeration cycle. So those are the formula of efficiency. Now if we would like to define if we like to define the second law second law thermal efficiency, then we can define in terms of Exergy. So in terms of Exergy, the definition would be eta 2 equals to Exergy recovered divided by Exergy expended. Which is equals to 1 minus Exergy destroyed divided by Exergy expended. expanded, right? So these are the these are the definition in terms of exergy. Wait a second, actually it looks like x, which is not true. It will be eta 2, right? So now we know that sometimes the ideal efficiency or reversible efficiency is misleading. The actual efficiency is different than the efficiency we just calculate from using the first law of thermodynamics, right? So this is all about the second law of efficiency. Now let's talk about the exergy change of a system. 8.4 exergy change of a system. We saw from the previous classes that if there is any thermodynamic process happening, or process, if a system undergoes a thermodynamic process, then several things changes. It changes the internal energy, kinetic energy, potential energy, enthalpy, it changes the entropy. So we saw that multiple things happening can happen in a thermodynamic system when it undergoes a thermodynamic process, right? Similarly, exergy also changes for a system when it goes through a thermodynamic process. So for the first case we would like to consider is that exergy of a fixed mass, right? So how the exergy is changing for a fixed mass, right? Basically closed system. So let me draw the diagram of a closed system, then it will be easier for you to catch. For example, this is a piston cylinder arrangement, right? That piston pressure is environment pressure is P naught, and then initial pressure was P, and then when it's expanding and going to the environment pressure, then it's becoming P naught, right? And then this piston is producing useful work, which is let me write it as a B useful, right? And then when this system is producing work or releasing the heat, then that heat is basically captured by a heat engine, right? Heat engine. That heat engine is basically producing some work as well, which is delta W heat engine, right? And when this heat engine is producing, then it is also releasing some heat in the sink, which is at, let's say, T naught temperature. Okay, so now we know that a heat engine operating between two reservoir, one is at this system, like this piston cylinder, another is the sink, right? And piston cylinder is also a work producing device, and this also engine is also producing some work. So if we do the energy balance, then we'll see that from the energy balance, is nothing but delta E in minus delta E out equals to dE of the system, right? dE of the system. So basically net energy transfer by heat work, and the net energy change, maybe it could be internal energy, kinetic energy, potential, or maybe enthalpy, right? So basically if we take a look in this entire system, then what is happening? So the change in heat delta Q, why negative Q? I mentioned in previous classes that when the work is producing by a system, then it's a positive, and when a system is releasing the heat, then it's a negative. So that's why it's negative, right? And then E out, which is delta W, right? And the total system, everything is a closed system. That means this gas system here, it's a closed system, right here. It's a closed system. It's a non-flow system. In that case, closed system, no kinetic energy or nothing is changing, or maybe changing, but in closed system mostly it is dealing with the internal energy change. That means du, right? Change in the internal energy. Now from a closed system, for a closed system, actually this piston cylinder arrangement, we know that work, right? With the definition of the work. So if it is a closed system, then the definition of the work equals to P dV, right? But if we can write this equation in just like this, P minus P naught dV plus P naught, dV. Basically we can omit these two terms, P naught dV and P naught dV, right? And it will leave only P dV, which is this term. Now if we see that delta W equals to this P naught dV, P minus P naught dV, this is actually delta W be useful work plus P naught dV. How? You can see that when it's changing the pressure from P to P naught and changing the volume from this state to for example from this state to it's coming to this state, right? So this is 1 and this is 2. Then when it's changing the volume, then it's also producing some sort of work. So that work is basically the useful WB useful works, right? So we got the value, or we got some sort of equation for delta W, right? Now we from the entropy chapter, just one thing I would like to mention here. From the entropy chapter, we know that ds equals to q dq delta q over t. So from chapter 7, right, we learned about that one, or we derived this relationship. And also the thermal efficiency, we just talked about in the previous topic. Thermal efficiency, it's basically 1 minus T naught over T, right? So now if we define the efficiency of a reversible process, then what is the of this heat engine efficiency? What will be the efficiency? The efficiency is the work done, or let me write it here. Efficiency of heat engine equals to delta W divided by actually it will be delta Q in, right? Delta Q in, right? So that's the relationship efficiency equation for this one. So now if we write this expression, right? So for example, thermal efficiency of that heat engine equals to 1 minus T naught over T, which is equals to delta W divided by delta Q, right? We can write this expression just like this: delta Q minus T naught over T delta Q equals to delta W. So basically it will be, actually let me write it in heat engine, right? Heat engine and heat engine. Okay, so from we just saw that this relationship, which is equals to ds, right here, ds equals to delta q over t, right? So if we write all of those, let me write it this way: delta W heat engine, which is equals to delta Q of heat engine minus T naught time ds, right? We can write it just like this way. So that means the delta Q of the heat engine, delta Q of that heat engine will become the delta W of heat engine minus ds, right? So that's the relationship. So now we know that delta W, right, delta W expression and delta Q expression. So let's plug in all those value in this equation number, let's say 1, right? So from equation 1, from equation 1, if we plug in all those value, then what we'll see. But before that, let me write it, the total amount of work, because you can see from this diagram two different work is producing. One is that useful work right here, useful work right here, another is that heat engine work. So what is the total work generated or work producing in this system? So delta W total useful, which is equals to delta W heat engine plus delta W B useful, right? So we saw that delta W heat engine equals to minus actually this useful work is equals to the delta minus du minus p naught dv plus t naught ds. Basically I just plugged in the useful work and heat engine work value in this in the equation 1. So equation 1 becomes like this, total useful work, if we would like to determine. So that means if we take the integral, then W useful as well as total useful work will be du means that change of internal energy U minus U naught plus P naught minus V minus V naught minus T naught of S minus S naught. So that's the expression of the total useful work of the system if it undergoes a reversible process, right? If for a reversible process and reached to a dead state, right? So that's the relationship between the change in internal energy, volume and entropy, and the useful work of a non-flow system, right? For a closed system, we also know that, let me write it. For a closed system, it may have kinetic energy, potential energy, right? It may have kinetic energy and potential energy, and the total energy will be the sum of total energy is equal to the sum of its kinetic energy, potential energy and internal energy, right? So that means that expression of Exergy X equals to change in internal energy plus change in work B minus B naught plus and change in entropy T minus S naught plus change in Exergy, which is mv to b square divided by 2, and change in potential energy m z, right? So for unit mass equation will look like small x, or actually for entropy for Exergy they define it phi, for unit mass phi, which is u minus u naught plus p b minus b naught minus t naught equals to s minus s naught plus v square divided by 2 plus g. So that's the expression of the Exergy, right? So now if you have multiple like if you would like to see the exergy change between two state, right? So for example, initial state to a dead state, then the exergy change will be delta x equals to x2 minus x1. Then it's very simple relationship, which is basically mass of phi 2 minus phi 1. And if we write this equation, it will be nothing but e2 minus e1 plus p naught of v2 minus v1 minus t naught of s2 minus s1, right? Or if you would like to write them in terms of internal energy, right, you can write that one too. So u2 minus u1 plus p naught of v2 minus v1 minus t naught of s2 minus s1 plus m v2 square minus v1 square divided by 2 plus m z2 minus z1. So that's the relationship between the exergy change between two state, like exergy change between initial and dead state, right? So one more statement or one more conclusion is that exergy of a closed system number one is positive or zero, right? However, it cannot be or never negative, right? This is very important. So from this expression we can see that exergy of a system, exergy change or exergy of a system, it could be zero or it could be a positive value, but there is no way that it will be a negative, right? So this is very important statement about the exergy. So it cannot be negative, and either it is always positive or zero. Okay, system is always either positive or zero. It cannot be never negative.